So today we're going to go through an introduction to regression. So we're on lecture 4 material. There's one more announcement for today, which is that there will be a new to the major event on Wednesday in the Meldrum lab from 4 to 5:30 p.m. So conveniently just after our quiz on Wednesday, quiz number 2 on Wednesday. Is feedback that we always get, or we often get from students who are non-traditional in some way, is that they find it hard to meet other people in the major in chemie, and that can be an important way to make sure that you have help on homeworks and this kind of thing. And so this is one part of our effort to try to improve that. Yeah, great question. So can someone who knows where the Meldrum lab is explain where the Meldrum lab is? Yeah. MEB. MEB. So MEB. Yeah, so in the basement. The other engineering building, where the department is, in the basement is where the Meldrum lab is. Yeah. So it's where you would have had 1703, 1705 if you had 1703, 1705, which I suppose is part of the problem if you are new to the major. So yeah, go ahead. Okay. Got it. But you know where it is then. Great. Anyway, so I encourage, this is, and just a note, this is not just for people who are new to the major. The idea is to connect people who are new to the major with people who are not new to the major, so it's open to everyone, including faculty. So I'll stop by after the exam as well, not to put any pressure on you. Yeah, so it's open to everyone, but it is part of a way of trying to help everyone make connections. All right, any questions before we get started? So today we're going to go over this material on lecture 4. Yeah. So quiz is going to be lecture 1 through 3. So quiz will be on materials. So quizzes will generally not be comprehensive. This first one is still including material from lecture 1, because in lectures 2 and 3, if you remember, we covered mostly Python. And so also I feel like quiz 1 comes really fast, and so I'm giving you another chance to look at the material from quiz 1 on quiz 2. Yeah. Other question? Yep. It's going to be more or less the same. I will send out the equation sheet for this quiz. Yeah. Yep. Today's lesson is not on quiz number 2. Yep. So that way you have a little bit more time to prepare. Yeah. Yep. Yeah, you should pull out that number. Yeah, and display that number, and that should be okay. Yeah. Yeah, there are multiple ways of getting, and actually one of the themes of today's lecture, we'll talk about linear regression, we'll talk about the theory of what linear regression is, then we'll talk about ways of doing it in Python. I think we'll show 4 different ways of doing the same problem, more or less, in Python. So yeah, and that's fine. Any of them are fine. Yeah. Other questions? Okay. So then yes. Oh, I mean, the new to the major event is the one that is right after our quiz. The new to the major event is this Wednesday. Yeah. Got it. Yeah, sorry. Okay. Other questions? Okay. Great. So now we're going to talk about regression, linear regression today. And as I said, we're going to go into kind of the theory of what linear regression is. One way to derive where it comes from, like what we're actually doing when we compute a linear regression. And then we're going to go over some examples of how to do it in Python. So, another definition, I guess we've talked a lot about definitions of statistics, but another definition of statistics would be study of how best to collect, analyze, and draw conclusions from data. And linear regressions are one tool that we can use to try to draw some conclusions from data. You've seen on your homework, we asked you to look at, basically plot some data as a semi-log, right? I believe this is homework 2, plot some data using semi-log axes, and you could see that it was a straight line, and then from that derive what the relationship is, right? From the fact that it looked like it was a straight line. With a linear regression, we'll be able to look at data that's noisier than what you were given in that example, right? Real data has noise. We'll look at data that has noise and how we can say, is it a straight line? And if it's a straight line, what's the best way of defining the parameters that define that line, or finding the parameters that define that line in some way that is statistically meaningful? Okay, so this will be a way of drawing conclusions about real data. So down here, we're going to have, we're importing data that is going to be on, for some process, extraction time versus extraction efficiency. And we're given this question of, what is the extraction efficiency when the extraction time is 35 minutes? So open question here will be, what's the best way to do this? What's the uncertainty in our estimate? And we're going to use our knowledge, or what we're going to learn today about linear regressions, in order to address this. So we're importing our libraries more or less as before, with some additional ones, for example, stats model, which we'll talk about towards the bottom. But here's our data. It's given, we're going to be importing these as NumPy arrays. It's time in minutes, right? Extraction time in minutes, and extraction efficiency as a percent, right, corresponding. And so here is a table, right, showing those two, showing that data, right, that we collected from for some process. And we can think of this as, maybe we ran this number of independent experiments, and each time we ran for a different amount of extraction time and recorded what the extraction efficiency was. So now we're asked, okay, what is the value at 35 minutes? And you see, we did have one trial at 35 minutes, right? So maybe the first thing you might want to do is just pull out the efficiency from that experiment that corresponds to 35 minutes. But this is real data with real noise, so that may not be the actual best answer, right? So what we want to do, and one of the things we'll be able to do with this linear regression, is actually incorporate all of this data to get a better understanding of what we actually expect on average at this 35-minute time interval. Does that make sense? So we're not going to get an answer that's exactly that, 62%. So we're going to plot the data first to see what it looks like. All right, we went over this in lecture 2. Plotting the data is often a nice way when we have, especially when we have time series data. Plotting it is a convenient way of understanding generally what it looks like. And so this is what that data looks like when we plot it. And we can see it looks like there's some kind of upwards trend here, right? Where extraction efficiency is increasing with extraction time, which you might expect, right? The longer we, the longer our extraction process runs, the more product we get out. But we would, now if we're trying to answer this question of what do we expect to see at 35 minutes, I think you can kind of get a sense from this about what the range of noise is in this data, right? It's not just a straight line, there's kind of some spread to the data. And so just taking that value that we measured at 35 minutes may not be the best estimate of what we would really expect kind of on average. So it looks like a straight line. So from this, we can say it looks like a straight line will do a reasonable job of describing the data. So we might write out the equation of a straight line. Y is equal to A naught plus A1 times X. And in some sense, then we've reduced this problem to trying to figure out what are the best values for this equation, right? What are the best values of A naught and A1? You with me so far? Okay. And then, right, our original question here is what is the efficiency or expected efficiency at 35 minutes? And so if we know what our values are of A naught and A1, then we can plug in and come up with an estimate for the value at 35 minutes. And again, an estimate for the efficiency at 35 minutes that incorporates everything that we know from all of these experiments that we ran at multiple different extraction times. So we're going to start this to set this up and understand where linear regression, as we normally define it, comes from. We're going to start with a simpler case where we don't have all the data that we're considering here, but let's just say we had 3 measured points, x1, y1, x2, y2, and x3, y3, right? Corresponding to three measurements of three distinct time points, let's say, x1, x2, and x3. In general, when we're talking about a linear regression or a fit to the data, what we're going to try to do is minimize the sum of the squared deviations from between the prediction, between the model, like our line fit, and the actual data that we measured. So the way we write this out is, so we're going to say the error. So this will be the thing that we're trying to minimize is this E error. It's going to be, first of all, the error, the difference between our point, y1, and our model value that we would compute from the linear model, again, with A0 and A1 that we haven't found yet, that term squared, plus the same thing, again, the value that we measured, y2, minus the value that comes out of our model, squared, plus the same thing for y3. Right, so this is how we're going to define. We're saying, we'll often call this, what we're doing today, a least squares fit. So we're going to try to find, in this case, the values of A0 and A1 that minimize the error, this E, which is written in terms of the sum of squares of differences between the observed values and the model values. Right, and here we've written it out all the way for just for three individual values that we have measured. With me? Where am I losing you? Some of you. No? No one wants to say anything? Okay, so this is how we're going to describe our error for least squares fit, again, just for the case that we just have three data points here. Right, so you can see another way to write this, another way to think of this. This is the actual measured value at y1. And for some set of parameters, A0 and A1, this is what our model would predict we would see at y1. So it's like if we draw in some line with a given value of A0, intercept, and slope, and we plug in our extraction time, this is what that line would predict for the extraction efficiency. We're comparing that to what we actually measured for extraction efficiency at that value and squaring the difference between those two. So if we have this expression for the error, and now we want to minimize, we want to find the minimum value of that error, we're going to basically look at the derivative of that error, that E squared, and set it equal to 0, right? So we're looking for some local minimum of this error term, defines this kind of big surface in terms of A0 and A1. And we know from calculus that if we're trying to find the minimum of some function, right, that's just some function of A0 and A1, we're trying to find the minimum of that function, we can take the derivative of that function and look for where it's equal to 0. That'll help us find a local minimum or local maximum. So we're going to take the derivative of that error with respect to A0, the derivative of that error with respect to A1. We can find those analytically, and we're going to set those equal to 0. Yeah.
How do you know that they're finding
Yeah, that's something that we would have to check. In this case, one of the reasons we take the square, we tend to do it in terms of sum of squares. That tends to be well behaved. We generally get a minimum here. So you'll have to take my word for that we're going to get a minimum if we set these equal to 0 for the way we've defined this. But that is a good question. So if we take these expressions and we rearrange them, we can condense them down into, right, so we end up with a system of equations for A0 and A1. And we can rearrange them to give this expression here. 3A0 plus the sum of xi times A1 is equal to our sum of yi. And the sum of xi times all our times our A0 value plus the sum of x squared times A1 is the sum of xi times yi. We can, so each one of these sums here is a sum from 1 to 3, because again, we're only considering 3 data points so far. We can rewrite this if we'd like to in matrix form, again, to help simplify this a little bit. One thing that this form really shows us is that, so if you remember how to unravel this, right, in matrix form, we take this row times this column is equal to this first value here. This row times this column is equal to this value down at the bottom. But one thing that the matrix form highlights for us here is that we know everything in here except for, right, given our set of 3 measured values, xi and yi, we know everything except for this A1, A0, and A1. So we know n, we know the number of data points, right? In this case, we're starting out with 3. We can compute the sum of all the x's, right? That's just the sum of all the extraction times. Here again is the sum of all the extraction times, sum of xi. We can compute the sum of all the extraction times squared, right? So just take all of the individual values, square them, add them up. And on the right-hand side here, we can again compute the sum of all our y values and compute the sum of the product of all our x values times our y values, right? Just by going through all those measurements, right? We could plug in all of these values. And the only thing we're left with is our A0 and A1, the 2 things that we're trying to solve for. And if you were, another thing to note here is, so we were talking there about 3, but here now we've generalized this. This actual form works if we have n data points. So any number of data points, not just 3, we end up with the same expression. But again, we know everything in here. We know everything in here, right? Because we know what the data is. In this case, we're given the data. We're just trying to find this A0 and A1. And so this tells us that we can solve then for A0 and A1. So one way of writing the solution out that we'll see is in terms of these parameters. We'll say SXX, SYY, and SXY. You'll see these written out in the solution, in the way that we define our solution, as well as the way that we define some of the summary statistics that we'll talk about. We'll talk about uncertainty, for example. And so we'll use this notation when we're talking about uncertainty. This SXX is the sum over all of the data points of the data minus the mean, the sample mean squared. SYY is the sum of over all the individual data points, each individual data point minus the sample mean of y, something squared, and sum of xy is the product of the differences between the data and the sample means. And then from that, we can solve for, from those definitions, we can then solve for and write out our A0 and A1 in terms of these parameters, where A1 is SXY over SXX. A0 is Y bar, the sample mean of Y. In this case, it's the sample mean of our extraction efficiency, minus A1, which we found here, times the mean time, the mean extraction time. Okay, or the mean of X. And again, in this case, I'm using X and Y to denote X to denote the random variable that is our input, right? Y to denote the random variable that is our output. But we know X and Y. We measured X and Y, let's say, in this example, right? So we're not solving for X and Y, we measured X and Y. What we're solving for here, so we can compute all of those things, SXX, SYY, SXY. We can compute all of those things from the given data. And what we're trying to estimate here are this A0 and A1. And so we can do so using those formulas. And what we've shown from the derivation is that, right, these formulas came from our derivation where we tried to minimize the sum of squared error, that E squared term that we defined just a few equations ago. And so by just computing these values, right, and our means of X and Y, we can find sort of, in some sense, the best value for the slope and intercept, right? The slope and intercept of our linear fit to our data, right? By just using the values that we had for our data set. So from this, right? So these define the least squares linear fit, or the linear regression to our data is then defined by these two parameters, A0 and A1. A1 being the slope and A0 being the intercept. Now from these, and we could then use these to look at the value at any given point, which we will do later, right? We'll look, for example, at the value at 35 minutes that we would expect to see. I should have put it in here. But we can then go a little bit further than that, than just predicting the value that we should see at any given extraction time, for example. But we can now start answering questions about, like, how likely is that value? What is the what are confidence intervals on that value? Like, what range of values do I expect to see at 35 minutes? And we can start to make statistical arguments about this data. So one thing that you'll often see is R squared. So you'll often see R squared as a measure of goodness of fit. It's called the coefficient of determination. And what R squared really describes is the proportion of the Y variability, or the proportion of the variability, in this case, in our extraction efficiencies, that's explained by the linear fit. So when we actually plot a line against our data, the line describes this fraction of the overall variability that we saw in, for example, here, the extraction efficiencies. And again, using these XY, SXX, and SYY, we can compute directly what this R squared is, right? So that's why we went to the trouble of defining those things earlier. We can also describe the variance of the vertical deviations. So what is the spread? This gives us a measure of what the spread is around the line that we fit to the data. Again, it's defined in terms of these SYY, SXY, and SXX. And we can then also look at standard errors, which give us an estimate of what our uncertainty is in those values A0 and A1, again, based on defining these parameters, right, of calculating these parameters from our known data. So this tells us, we'll define the standard error more properly in lecture 7, but we can use these standard errors, and we'll show that we can use these standard errors to do some additional analysis of our fit and check about confidence intervals on our fit in the code that we're just about to look at. So these standard errors, though, we can think of them for now as telling us about the expected spread or expected uncertainty in the parameters A0 and A1. They tell us something about the uncertainty that we have there. So, and this is what that looks like. So we can define a confidence interval, and again, we're going to formally define confidence intervals, but we can think of it as saying something about the range. Confidence interval for now tells us the range of values that we would expect to see from a set of experiments. And so for our A0 and A1, those confidence intervals are defined as described here in terms of the standard errors that we would compute for A0 and A1, multiplied by this t statistic, which again, we're going to be discussing in lecture. But the thing to take away here from our current discussion on linear regressions is that the values that we compute for A0 and A1 are estimates. Those estimates have some uncertainty, right? Like, we do not know them perfectly. Those estimates have some uncertainty, and we can actually define what that uncertainty is. And this is how we define what that uncertainty is. So let's go back and look at that data, and we're going to do so with some code. So this function here, right, that's defined in Python is computing those different statistics that we described analytically just above. So you'll see that we're taking in some set of values x, some set of values y. So these would be like our measurements. And then we're going through and we're using NumPy to compute the mean of x, the mean of y. We're then computing SXY, SXX, SYY as defined again up above previously analytically. And then we're going through, we're defining the slope, the intercept, just as we found analytically up above. We're finding the R value, R squared value, which is that fraction of or proportion of the variance in the data that's explained by our line. And again, going through and describing all of our other parameters, right, that we had, that we described analytically, right? So this is just going to return all of those parameters as this big array, right? It's just doing all those calculations in Python, returning them as a big array. And when we do that, so we're going to take all of those values, we're going to put them into an array that we're going to call linear here. And we're using that function A1 and A0 that we just described with our data X and Y that we measured, right, for extraction efficiency versus extraction time. And then our code here is just going to plot or print all of those different values. Sorry, not plot, just print them all. And we can see we found our best fit values for intercept and slope, 39 and 0.764. We have the sample correlation coefficient, which is R, and the coefficient of determination is that R squared value. Measurement of goodness of fit was 0.68. This is generally a pretty reasonable R squared value to have for a linear fit. And again, we have all of these other statistics for our linear regression calculated for us in Python. Okay. We can, so we could also then go in and look at the value, right? Our original question was, what is our expected value at 35 minutes, right? So we can compute our expected value at 35 minutes. And this should just be our A0, sorry, it would be our slope linear of 0 times 35 plus linear of 1 should be 35. And if we just run that, right, we'll see that we expect, and that can't be. Huh. That obviously can't be. Got it. That's correct. Thanks. 65%. Okay. So we see that we expect, right, thank you. Our answer to our original question of what is the expected value of the extraction efficiency at 35 minutes is 65%. We can compare that actually. It's interesting to then go up and compare that to our measured value at 35 minutes. We saw that our measured value at 35 minutes was 62%, right? So that means that our measured value at 35 minutes was a little bit low relative to what we would expect, again, based on knowing the rest of the data that we have here. Okay. But we can go a little bit further than that, and we can start putting, we can use what we've computed or what we know how to compute now for our linear regression. And we can use that to place confidence intervals on our resulting calculation. So we can say, right, so we computed that we expect this 35.7%, sorry, 65.8% at, we expect 65.8% extraction efficiency at 35 minutes based on a linear fit to all of our data. But how close do we expect the value to really be to that number, right? Do we expect to see 65.8 plus or minus 0.2%, or do we expect to see this plus or minus 10%, right? Like what's the range of values that we would expect to see within a given experiment? And so that's what we're getting at when we're talking about confidence limits here, or confidence intervals. And we can compute those confidence intervals using the estimates that we have up above. For example, here, this would be the confidence interval on our estimated value, A0 plus A1x, is given here, where again, it's defined in terms of that standard error, as well as this t statistic, which we are going to talk a lot more about in lecture 8. But for now, we can say that this is like a coefficient out front of our confidence interval estimate that tells us something about that's based on, for example, how big the sample size is. And so from this, we can compute the 95% confidence intervals, which is done here. I just want to skip ahead to the plot, where this is telling us this is showing us the original data in red. The line, that's our least squares fit, our A naught plus A1x, right? So that was when we said we plugged in at 35 minutes and we asked, what is the estimated value at 35 minutes? That's the value that just lies directly on that line. But now we can also place confidence intervals on our estimated values. And that's shown in this dashed line, right? This kind of curved dash line there shows us the confidence intervals. In this case, it was 95% confidence intervals. So that means that we expect about 95% of the data to lie inside of those two curved lines, above and below that fit. So we don't expect to see that many values lying far outside of those lines. And then the last thing that we have to find here are the limits of prediction. So this tells us so the limits of prediction are going to be based on the error, the uncertainty that we have in our A1, A naught, and A1 itself. So it's more or less like how uncertain are our A naught and A1 values themselves. And that is defined down here, or that's shown down here as these dashed dot lines as well. So taken together, this gives us an estimate of what we expect to see, right? Is that solid line on average, what we expect to see based on incorporating all of the data that we have into a single estimate of the linear fit. For a given value of the extraction time, what is the range that we are most likely going to see? It's going to be these curved lines on either side. And then based on our overall data, based on our A1, A naught, and A1, what are the limits, or what is the uncertainty in those A naught and A1? Like, we expect that the line, based on this data, we expect that the true line, this is really just an estimate of what the linear estimate is between these two expressions. So the true line that falls in the middle of this data could be somewhere in the middle of, should probably be somewhere in the middle of these outer intervals there. I feel like that point's not landing. So let me see, what can I help with? Is there something here that I can try to explain a little bit better? I feel like that explanation is not really working. Yep. And you run everything else up above that code as well? Okay, let's see if we can find var-e. You know, I did move a different piece of the derivation down below. Yep, here it is. So the variance of error is defined down below. That needs to be defined above. And I think in my code, it doesn't have that dependency. So that if you run the cell, yeah, sorry, that should be fixed. But if you run the cell down below in the derivation piece that we're not covering, then you should have that var-e and you should be able to run it. Okay, so that should resolve at least that issue. All right, so if I asked you, so is it running now if you get that very defined? All right, I'll let you try that. But I want to ask, so if let's say that, so we were talking about 35 minutes. So if I asked you for if we run this experiment for 25 minutes, what is the value that you're going to, and I guess I'm going to ask for raise of hands, and there are going to be three answers, three potential answers. One of them is going to have to do with the solid line, one of them is going to have to do with the dashed line, and one of them is going to have to do with the dash dot line. Okay. So if let's say we're at 25 minutes, so we want to run our process for 25 minutes, and I ask you, what is the expected value that you're going to see, or the average value you're going to see for extraction efficiency if you run your process for 25 minutes? Are you going to find that using the solid line, the dash line, or the dash line? Let's see, solid line hands for solid line. Yeah. Dash line, dash dot line. No, right? So the expected value that we're going to see at any given time point, right? The average value that we're going to see at any given time point is what's shown by that solid line, that linear regression line. Okay. Now let's focus on the 25-minute here. And now I want to know, what range of values would you expect to see if you run this experiment multiple times, right? At 25 minutes, you run an experiment at 25 minutes of extraction time over and over and over again. I want you to find the range of values that you expect to see at 25 minutes. Are you going to use the solid line? Let's see hands. The dash lines? Let's see hands. Or the dash dot lines? Okay. So you actually use the dash lines. So the dash lines here are showing our confidence intervals. So that's for a given time point, what is the range of values that we expect to see? That's given by the dashed lines. Okay, that's how we define that. Yeah, so we're expecting 95% are within that range, right? So there might be a bigger range than that, but this describes where 95% of the values would be, which is typically a reasonable estimate. So is that the confusion? So it's not that all values are necessarily within this. It's that we expect about 95% to be within that range. Okay, so this would be a reasonable estimate for what the spread we would expect to see in the data is. And the reason we don't use the full range, 0 to 100%, because in real data, we almost always have, or we often have outliers that go far beyond that range. In this case, we have some outliers that went a little bit beyond that range, right? Yeah, and so that 0 to 100% range might be infinity, minus infinity to plus infinity. So we typically look at a narrower range, and 95% is what's often used in statistics. Okay. So if we're asking about a specific value and we want to know what are the range of values we expect to see at that specific, for example, time point, what is the range of extraction efficiencies we expect to see if we run the experiment a bunch of times, that's this confidence interval. Okay. Now the third piece, right, I asked you to raise your hand for 3 different categories. So the third one is going to fall into this third category. So we'll just skip ahead to what it means. So the third piece has to do with our line itself, right? Like we made a certain number of measurements, and then we estimated this, a line passes through all the data. But that line itself has uncertainty. Like we don't, we only made 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 measurements, right? So what these outer lines are showing us is we don't know exactly where that line itself is terribly well. And so there's uncertainty in where that line could be. So if we run this experiment a whole bunch of times, we might end up with different values of what that linear fit is. And this is giving me a confidence interval on where that line could be from what I know. Okay, does that make sense? So it's the average value of the data, the range that we would expect to see at a given point of the data, and then uncertainty in our model itself. Yeah, first red. Yeah. yeah, then the range we would expect to see based on that model would move as well. Yep, that's correct. Yep.
Why is the
Yeah. Well, one thing you'll notice that all of our SXY, SXX, SXY, all these things, they're all based on differences from the mean. And so what this is really telling us is that, or what it's showing us, is that we have the best idea of what our function looks like towards when we're close to the center of it, when we're at the mean value. And as we get to extremes, we don't have as good of an idea of what those values are. Yeah, so we just have a better idea as we get towards the center. I mean, another way to think of it is like if we had the slope a little bit off, right? If our slope was off by just a little bit, it wouldn't actually affect the values in here by that much, but it would affect the values out. It could affect the values outside by quite a bit more, and so that's what's captured here. Yeah.
so where the cause
That's the tighter the spread. That's where we would expect to see, yeah, more. It's a better estimate, yeah. So if you were designing an experiment to measure efficiency, extraction efficiency around, so let's say 35 minutes, right? Then this is a reasonable experiment design, kind of, centering that in your range. But if you were designing an experiment to understand what the extraction efficiency is at 20 minutes, right? You probably want to be measuring more values around this, or you probably want to center your measurement interval on that. That makes sense. Yeah. Yeah. With more points, your uncertainty in all of this would become less, and your limits of prediction in particular would get a lot better. Yep, definitely. Yeah, I mean, one thing to take away from statistics, generally more data makes your statistics better. So, but oftentimes we're limited in money, time, other things. So we have what we have. Other questions? Okay. All right, so here, now we can answer this question of what our expected extraction efficiency at 35 minutes is a little bit more precisely. And we'll say at 35 minutes, we know the extraction efficiency we computed previously of 65.8%. And here we're also putting 95% confidence interval, so plus or minus 5, right? So we have a reasonable estimate of what our extraction efficiency is. Another thing that we should do whenever we have a model that we're using to predict our data is check to see if that model is capturing the trends in the data. That's what we mean by checking the adequacy of the model. So we looked at the data and we said that a line looks pretty good here, right? But sometimes what you think looks pretty good isn't always necessarily the best model for the data. And one way that we can identify whether or not we have kind of a systematic error, or whether or not a linear fit is really describing the trends that we see, in this case, whether a linear fit is describing the trends that we see, is to look at the residuals. So the residuals are the difference between our measured value and the estimated value from our model, right? So that's what we mean by residual. So in this case, we're going to plot the residuals versus time, and that's shown here. So this is our residual versus time. So first of all, we want our residuals to be as small as possible. That means that we have a good model, and I don't know, they look. We know from our data the residuals are not huge, right? We know from the linear plot at least our residuals are not huge. But the other thing that we're really looking for here is there some other trend in this data set that we might be missing in our model? Like, is there some curvature or some other shape to this that our model is missing? And in this case, we can see that these points look essentially uncorrelated. Once we remove this linear fit to it, the data this is just a big mess, right? There's no real trend here. And so our model is probably describing the shape of the data. I think here's an example from my lab showing this, I think, a little bit more clearly. In this case, it's not a linear model that we were using. So we did least squares fitting not to a linear model, but to an exponential. And we'll talk more about fitting to other kinds of curves at a later point in the class, but we're fitting to an exponential. And what we found was that it's just data that looks more or less like a purely exponential kind of curve. By eye, it looks like an exponential curve. But when you do an exponential fit to the data and you plot the residuals, you see this kind of a shape here. So in yellow, you can see this kind of a shape where there's very clearly some kind of a trend in that data that's not being captured by that, that first fit equation. And so what we found was that you have to add a constant to it. And if you add that constant to it, then you get this nice absence of trend in the residuals, indicating that we seem to have captured what's going on in the data. If that makes sense. Yeah. 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 So basically, we haven't talked about how you figure out what that something is, right? But just that something else is going on, right? So if you fit a line to it and you plot the residuals and you see some kind of shape, then you know maybe a line was not the best, or maybe a line doesn't capture everything that's going on in the data. Yeah. Okay.
And then the second, I didn't feel like anything that's like full, which looks like the right so I don't know.
SOL, is it defined? Sorry, again, just before I uploaded, I moved a bunch of code to the bottom because I didn't want to go through the derivation based on linear algebra. So it's likely down at the bottom. You have to copy that whole chunk and put it up. Okay, so one way of doing this is copying the whole chunk and putting it up. Yeah, you can see here, sol is defined down here. Yeah, what I really need to do is rewrite this lecture and completely remove this. But in going through it, I thought that another derivation of linear regression was not actually helpful. So that's why I moved it to the bottom. Does that answer your questions? Yeah, okay. Other questions? Yeah.
What does the app operator do in Python? Okay.
Multiplies two matrices. Okay, thank you. Okay. And again, and that bottom derivation. So there's another way of thinking about what linear regression is and where it comes from, based on linear algebra, which is covered in the bottom piece of this code, which originally was at the top, which is why there's some dependencies. Apologies for that. Okay, so one thing that we would conclude by looking at residuals in this case would be that the model shown in blue is preferred because it doesn't have this kind of systematic error as we go versus as we look at the residuals in this case versus time. So there are a number of different ways of computing statistics for linear regression in Python. We're just going to look at a few of them here. So far, we've shown you one way, which is code it yourself, right? So we gave explanations of what the various statistical parameters are, or various parameters about the linear regression are in terms of that SXX, XYY, and so on. And so you can actually just define those yourself in code, or use the function that's already defined here in code and call that in order to compute this all in Python, right? Use it more or less like a calculator where you program it in directly. But we also, because linear regression is really commonly used, there are a number of different routines in libraries that can do this for you a little bit more quickly without you having to code it yourself. So one is in stats models. So stats models is another library that we can use within Python. This stats models works on a data frame. So remember last lecture we talked about pandas data frame. So this is something that we can do with, or we need our data to be in a data frame in order to work with this stats models. So we can take our data that was in these arrays X and Y and put them into a data frame. And again, we went over this last time about how we can take data and bring it in or out of pandas. So here we're putting data XY into a pandas data frame. We're using this pandas head function in order to actually just look at the beginning of that data and make sure this looks okay. And then we can then use this OLS dot fit in order to do our ordinary least squares fit to our model. And this is our syntax. We're saying that y is proportional to x. We have some linear relationship between y and x. And we're giving it this data xy. And then we're printing out model.summary, which gives us our results. Okay. So essentially all of that stuff that we showed Python code for, we derived up above. This is what it's using here to compute these statistics, along with some others that we haven't discussed yet. For example, a lot of these have to do with how we would more rigorously say that one model is preferred over another, that kind of thing. But from this, we can also see that we get values, for example, for the intercept and the slope, standard error on those values, confidence intervals on those values, right, are all computed automatically for us. This is telling us that we don't have enough data points to really do all of this stuff reliably, but it's still going to compute, give us those estimates. And now this model object that comes out of that OLS function, ols.fit, is contains all of the statistics about this fit. So it's all computed for us and stored within this model. And you can then try to look at what's in there. So we can say, I don't know, some other results is model dot. And now we can see that, there are a number of other different things that I can pull out, right? Degrees of freedom of the model, eigenvalues, the covariances. I can pull out what the model was. I can pull out what the parameters are. I can pull out predictions, or I can, there's a function that's defined here to actually make a prediction. So I can pull out my R squared. Let's just do that, is easy. So we can pull out, any different parameter that we want from this. Print other results. So, right, we can pull out other values from our model using the functions that are defined on that model object. So in this case, I pulled out what the R squared was, which again, we had computed up above, and it was about 0.68. So we get the same results. So just know that, so this is showing model.summary, but we can pull out any one of the values that we want about this linear regression. They're just stored within this model structure at the end of this calculation. So again, here we're pulling out A1 is model.params of 1, A0 is model.params of 0, and we can pull those out as well. We have, again, and the same thing here, we're pulling out confidence intervals for the slope and margin of error for the slope, all again pulled out from that set of parameters. We can do the same thing in stats models based on defining the data as an array. So if we define the data as an array, in this case, we're defining it as an array. We can print that out as shown here. And then we can use this. SM is where we imported stats models to, sm.ols, ordinary least squares of our data. And again, we're printing out our model summary, and we get the same results. Right, so another alternative way of doing it if we have our data stored in an array, or if we stick our data into an array. We can also use this sm.ols routine. So like this would be used, the data in data frames. Again, this is just another alternative syntax for calling our ordinary least squares fitting in stats models. But more or less, we're getting the exact same thing, where we're getting model fitted is model.fit, and we're printing that model fitted summary, and we're getting the same results that we did up above. I'm going through this maybe a little bit more quickly just to note what we have here as reference material for stats models, but slow me down if there's something you want to see more closely. Right, and then this is showing us how we can actually access the model parameters that come out of that. So in this case, here's model fitted.params, again, is where the parameters of our fit were stuck, and we can see those here. So another option, which is distinct from those, so all of those, we're using our stats models methods. We showed stats models on a data frames or stats models on an array. But we can also use our NP, right, just NumPy, so we don't have to necessarily, we're not stuck with using pandas for this. So we can use np.polyfit. In this case, we're saying that we're going to find our array of coefficients and a covariance matrix of the polynomial coefficient estimates. So something that tells us about the uncertainty in those estimates. And the syntax here is np.polyfit. So NumPy, right, was imported as an NP here. np.polyfit of our data in X and Y. This is telling us the order of the polynomial that we're trying to fit to the data. In this case, it's just a linear polynomial, so it's order 1. And that we're going to get our covariance out. And this is what we end up with, right? So we have our values plotted here. And then we can use this NumPy poly1d function in order to create a function or a polynomial that we can actually plot. And if we do that, we can then recreate this image shown here where we have the data along with that fit curve. And again, it's the same fit curve that we had, right? If you notice, if you were keeping track, those are the same coefficient that we got with the other methods as well. So that's where I plan to end today. Any questions on this? I know we went over a derivation of what linear regression is, some definitions of parameters that we can compute about a linear regression with an example of how we might use those, and then examples in code. Any questions on any of that? Yeah. I expect you to know how to use those expressions. Based on the examples given here, what we haven't discussed is a more in-depth description of what those mean, right? Aside from just an estimate of what the uncertainty is, we haven't talked about what the t distribution is, right? So I expect you to be able to use it, but you don't know precisely what the t distribution is yet, so I don't expect that. Yeah. Yeah, I would definitely expect that you now are able to find a linear regression line from a set of data. Yeah. Yeah, that's a good question. Let me get back to you. Yeah. Because yeah, the challenge is I'm trying to do it without, I know we talk a lot about code. I'm trying to think about what I'm going to ask you to do. Yeah, to test your understanding, but yeah. Okay, so quiz 2 is on Wednesday. It's covering material from lectures 1 through lecture 3. Any questions on that before we all break and run away? Okay. All right, so I will see you on Wednesday then for quiz 2.